look at this waveform. This is a simple sequence detector 101 FSM waveform simulation. Okay, so here we provide input 1 0 1 and our output is 1. Okay, and again 1 0 and 1, our output 1. But what is wrong here? It is wrong because this is not output, it is a glitch. So this is a Mealy machine, and why this glitch shows here we will see in this video. Okay, so welcome to the Silicon Learners. Today's topic is why Mealy FSM shows glitch and Moore does not, and when you have to use which type of FSM. Okay, so let us start it. So basic of Mealy machine and Moore machine is Mealy machine depends on state and input both. Means when the output changes, it is depends on state and inputs. Okay, where another side Moore machine, its output depends only on the current state. So our current input can't change our output. So in the Mealy machine there is no clock gate, immediate clock gate. So that is a reason in the Mealy machine glitches occurs, and Moore machine gated by state register, not the clock. So gated by state register, so it is a glitch free. Okay, so here how Mealy hardware works and Moore hardware works in shows in this diagram. Okay, so Mealy hardware, in the Mealy hardware when we give input, the next state logic occurs. Okay, and next state logic will be move ahead with the current state. Okay, but it is clearly shown at the next state logic output logic will be occurred. Why? This is because we give input and combinational path from input to output, and at Moore hardware we observe that output only from registered state. Means output of the Moore hardware depends on the current state, and output of the Mealy hardware is depends on input and current state both. So if we change in input, our output also can be changed. So here the one experimenter shows, in the experiment 2-state FSM we write in the both style Mealy and Moore. In the this is our FSM specification where we describe our two states, one is idle and one is active. Our input is enable and output is done. When the enable equals to 1, transition will be occur and it is a idle state. When enable equals to 0, it will be idle state, and when enable equals to 1, it will be active state. Okay, so in the Mealy machine here we defines our always block. When we provide enable signal, means our input signal output change with enables, means it shows Mealy depends on the input, and when we gives input and the output change, it will be changed immediately. It is not depend on clock. And on the other side Moore machine is depend on clock edge and state both, means clock edge with state. This both blocks shows clearly. Okay, so this is a diagram of waveform how glitch occurs in Mealy machine, and how the Moore output is clean. Okay, so we will understand more with the waveforms. Okay, so let us go on it. So see this, here is our Moore code. This is our simple 101 sequence detector. We are described it in our previous videos. Okay, so this is our code and this is our code logic. Now in the code, here is our test bench. First of all, we give 101 pattern and the random asynchronous changes in the output. Okay, so let us see in the Moore machine we observe the glitches or not. So we will just open our simulation report. Okay, here is our all objects and we have to add it and just run it. So here is the waveform. Now observe this waveform. Unlike the Mealy machine, here not we see glitches. Here we can see clean output. See, for 1 0 and 1 pattern at the next clock edge, we can see our Moore output is 1. Where we see in the Mealy output the glitches comes. So this is all about Mealy and Moore. Okay, so question arises when we have to use and what are the real world impact, why this matters Mealy and Moore. So it is a impact on FPGA, ASIC and CDC. So here is a source in FPGA. Only 1 nanosecond spike also can interrupt handler and system can be crashed. All this happen because Mealy machine depends on current input and with the asynchronous inputs where we toggle asynchronously our input, it can be difficult in debug. At the ASIC side, it can violate setup or hold off downstream flip-flop. Metastability propagates through chip and silicon spine cost $500K plus in 3 months. Okay, and this type of mistake is clock demon crossing plus glitch. When these both mistake happen, it is a disaster. It is simply so. In the upcoming videos we will describe what is clock domain crossing and study about it. Okay, so this is a chain reaction when Mealy output glitch spike and then downstream flip-flop wrong state and system crash. So question arises when to use which, when you will use Moore machine and when you use Mealy machine. So and another question arises, Mealy is good or Moore is good. So this diagram shows when you have to use Moore and when you have to use Mealy. So Mealy machine basically used when you need faster response, fewer states and immediate output. You have to not use Mealy machine when a code is complex and glitch risk arise. Okay, when you need stable output and glitch free output, you must use Moore machine, and when the complex designs come in the face, you must use Moore machine. Okay, and this is a source best of both Mealy logic plus register output. It will give faster response of Mealy plus stability of Moore synthesizer, creates extra flip-flop at output. This is a one type of default choice. So here is summary about Mealy Moore. So does it mean Mealy is good, Mealy is bad and Moore is good? No, it is depends on our use, where we have to use. If we use Mealy in a faster response and required place, the Mealy will be good and Moore will be disaster. At the another side, if vice versa condition, then Mealy will be bad and Moore will be good. So it depends on user how it is used. In the next video we will show binary versus one hot versus gray encoding. This is our type of binary representation, means bit representation. Okay, thank you.